Hey everybody, MoNaCo here.
And Mills.
Okay, we're talking about atomic theory today. We are going to work on page 21 and 22 in our packet, as well as give you so much more knowledge than is just on the page.
Seriously.
We're going to learn how electrons fill in around the nucleus of an atom. We know protons, neutrons, and electrons exist, but how do they all get arranged together is the important part. So far, we've seen that protons and neutrons are in the nucleus, give the atomic number and mass, make isotopes, but what about these electrons? Well, how do they play into the picture?
Right. So this chart on the left illustrates the filling order for these electrons. It helps us understand a little bit about this electron configuration. 2, 8, 13, 3 for manganese, because it looks a little funny compared to some of the simpler ones that we see. With the orbitals arranged in this picture the way they are, the electrons are going to fill diagonally.
Now, this is actual quantum chemistry. This is the real deal, like Holyfield, like the big boy and girl version of like why atoms and electrons the way they are.
Right. The shapes of the orbitals.
The shapes of the orbitals are in here, right? We don't get into principal quantum numbers and stuff in this particular course, like principal energy level we will talk about, N,
right.
But we don't talk about quantum spin state, L.
No.
We don't talk about pairing, up
right.
and down. We don't talk about
Pauli
all that stuff.
Pauli
Exclusion, Hund's rule. Some online courses you might find that when you look up electrons and stuff that case, but we're just talking about the most basic electron configurations in our references.
So 1s is going to fill first.
Then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, then the 3d. So this pattern explains so much more in chemistry than we are able to get into right now. It explains why the periodic table is shaped the way it is.
Right.
It explains why certain elements react with other ones the way they do. But we're limited with our resources to teach you about the Bohr model electron configurations.
This is a lot simpler, easier way to just express what we see on the periodic table. So what we're going to show you is, or what you're going to show doing a Bohr model is the nucleus, and then just the electrons that are in the electron configuration.
In the principal energy levels.
And the principal energy levels.
Mm-hmm.
So and here's the other picture kind of shows that this is a lot easier to see pictorially what each atom looks like.
And it almost starts to look like a periodic table in itself.
Right.
So let's get into some of the details that actually make you need to.
These are vocab terms that we all need to know.
So electron configuration for a neutral atom is what's shown. It shows the number of electrons in each orbital or principal energy level, however you want to look at it, separated by a dash. Over on the right-hand side, we see the electron configuration from our previous notes. It's not 2 minus 4, it's 2, then 4. So the first innermost ring has 2 electrons. The second outermost ring has 4 electrons on it.
Excellent. Let's talk about that 4. 4 is what we call the valence electrons.
Mm-hmm.
So these are the outermost electrons, or the last number in the electron configuration. These are going to be the most important going forward. The whole unit of bonding is going to be based on just valence electrons.
Because they're the ones on the very most outside, right?
Right.
Which are the ones that would be the first to touch something else's electrons.
You got it.
Those ones on the inside we call something special called the kernel electrons. These are the inside electrons. They're the non-valence electrons, and they are tucked inside the outer shell of this atom, if you will, and so they're not reactive. They don't determine properties of reactions or chemicals, properties or anything for that matter.
Very little.
Very little.
Electron configurations for ions, it shows the number of each electrons in each orbital, of course, separated by a dash, but it varies from the base atom depending on how many electrons we gained or lost. So that number can change, and that's a game we're going to have to be able to play. Looking at the base that we see in the periodic table, if I see an electron configuration that's different for the same atom, then it's an ion.
It's got to be. And the ion will show you if it's a positive or a negative charge.
Absolutely.
Just remind me, Mr. Milks, if I have a +2 ion, that means I've gained 2 electrons, right?
No.
No. A +2 means...
It means I have 2 more protons than electrons, so I must have lost 2.
Oh, I lost 2. So that's going to come into play soon. And if I have a -2 ion, I must have gained 2 electrons. I have 2 more electrons, which are negative sign, than protons.
There you go.
Okay, so that neutral atom really has a lot to do with everything.
Right, well that's going to be our base, and we're going to go from there.
Gotcha. Now here's the principal energy levels.
The areas where electrons reside, they are filled in order. I always put 2 electrons in the first principal energy level, and then I'm looking for 8 into the second, and then again into the third.
And now when you say the first energy level, do you mean the one that's all the way on the inside, the smallest one, or you mean the one that's the biggest one all the way on the outside?
I mean the one that's inside most, one closest to the nucleus. Always starts with 2.
So we order from the inside out.
Right. And this whole thing, knowing that order is going to help us determine later on if an atom is excited or in the ground state.
Oh,
So
the electrons, yeah.
Rules.
We know these rules for sure. Okay, so let's get to some configurations. For magnesium, we're looking at my periodic table here. I look at the electron configuration for Mg, it says 282. Oh, wrote it down.
Beautiful.
Simple enough. Mr. Milks?
Now I have magnesium plus 2 ion. So, Mr. MoNaCo, plus 2 ion. Did I
have
my electrons?
I have 2 more protons than electrons, which means I lost 2 electrons from the outside-mostest shellist.
There you go. So I lost 2 valence electrons. So notice my electron configuration now is just 2, 8, and I lost the last 2.
Oh, so kind of like this. When it became an ion, those 2 electrons kind of disappeared.
That's right.
Oh, okay. All right. Well, let's erase that because that's not what we're talking about right now.
Okay. Let's do bromine.
Bromine. Let's see. The smart board's not working so great right now, so I'm just going to tell you what the configuration is. I'm looking at my periodic table. I found Br for bromine. The configuration sequence is 2-8-18-7. 2-8-18-7 for good old-fashioned bromine neutral atom.
Okay.
Mr. Milks, how do we do the Br -1?
Well, first I got to figure out -1. Does that mean I gained an electron or I lost?
Oh, not this question again.
This question's going to happen every time we get ions. So, but
Br -1. -1. There's one more electron than protons.
There you go.
So
I must have gained an electron.
I gained one more.
Right.
Right.
So my original base was 2, 8, 18, 7.
And
so if I gain an
one more electron, it's going to go on the outside ring.
Got to go on the outside. That's where it's going to fill, because the other ones are all full. So now it's going to go to 2, 8, 18, 8.
Gotcha.
1.
Okay, so 2-8-18-8. Cool. Now for barium, Ba, barium. Whoa, long sequence. I'm reading it off the periodic table, though. There's no ion here. 2-8-18-18-8-2. My gosh, how many circles of electrons are on there? Looks like 6.
So that means there's 6 principal energy levels.
6 rings of electrons. Okay, got it. Okay,
good.
Now lead. If I look at my periodic table, hey, Mr. Milks, look right here. What's wrong with that?
Well, it's missing on the periodic table a whole bunch of those first numbers. It's missing the 2, 8.
Oh, maybe because there got to be so many circles of electrons, they couldn't squeeze them all into the box.
Right.
Okay.
I think so. So I think that star designates the shortcut.
Right. It's a shortcut, yeah, for 2-8. So for lead, it should be 2-8-18-32-18-4. Oh,
Yeah.
man, imagine having to draw all those circles with all those electron dots on them.
Sounds like a homework assignment's coming.
Or a nightmare, one of the two.
Yeah, something like that.
So now let's look at kernel to use a shortcut. That star was the kernel to show the inside electron. So we're looking at chlorine. Now remember, we're going back to valence and kernel. Valence is just the outside electrons. So the last number in the sequence. Not the first, but the last. So chlorine had a 2-8-7 sequence, which means the valence ones are the outside ones, which are the, Mr. Milks, help me out.
Outermost? No, would that be?
The 7, the outermost. You're right. And the kernel ones,
all the rest.
All the rest. But it says 2-8 and this is 10. How did they get?
Well, because there's 2 in the first and then there's 8 in the second. Add that up.
Get 10.
I get 10.
Gotcha. Okay, I think
Let's do that again.
let me try this out on nitrogen. It says on my sequence here, the electron configuration is 2-5. So valence is the last number.
So that's 5.
That's 5.
Yep.
5, write that down. And kernel is everything else, but there's only 2.
So then that's it. 2.
I don't have to add there?
There's nothing to add.
Okay. So 7 doesn't play anything into it.
Well,
No.
there's 7 total.
Total. but 2 in the first ring inside,
Right.
5 on the second ring outside.
Right, and then because it's the outermost ring, then now that's balance.
All right,
Right.
so why don't you try the last one, Mr. Elk? Sodium. Mhm.
Okay, well, I'm looking at the electron configuration, and I see the electron configuration is 2, 8, 1. Valence is the outermost.
So that's the 2, right?
No, that'd be the innermost.
Oh, so it's the 1 then.
You got it.
So
Outermost.
1 valence electron
The last,
for sodium.
the last one. So I have 1 valence electron. The kernel then, I have a 2, an 8, 1.
2 minus 8 is negative 6.
Very good, but I can't have negative electrons, so I want to add those.
Oh, but it looks like a negative sign.
But remember, that's not a negative sign. That's just a dash separating the principal energy levels.
Okay, so 2 on the first level, 8 on the second level, 1 on the third level.
Correct.
And the third level is 1, it's the valence.
It's the outermost.
So the the kernel electrons must be 2, 8, 10 total.
You got it.
Okay.
10.
Man, I get this kernel and valence messed up all the
Right.
time.
Well, the key is the balance.
Okay.
So as long as we get the balance right, we can add up the rest to get the kernel, and we should be good.
Now, I will let you all know that if you go out there and look for electron configurations on the internet, you're going to find quantum theory. You're going to find P, L, M, all that N level. It's going to be very challenging. New York State and our class is unique in the way that we do this. So this is the time where you maybe have to go and find us on the lunch period to really help you understand this.
Sure,
You
if
don't
you're
get
having
it
trouble, because
after we've done the
you don't want to be
practice in
convoluted
class.
with that P, D, F. That's talking about shape and all this other stuff that we don't really need to get into. But you do need to know what valence electrons are. You do need to know what principal energy levels are, and electron configurations and how we're going to, use those.
Yeah, and we're going to get into using these things to draw models
I think
of
next
atoms.
notes.
Excellent. Thanks everybody for watching.
See you in class.